Video 1 of Chapter 10. We are going back to confidence intervals, but this time around we will be doing confidence intervals for means. Video 1 is specifically just going to look at a one-sample confidence interval for a mean. Now, we're going back again to confidence intervals back in Chapter 8 when we did them for proportions. And the main idea of a confidence interval still applies. We start with a point estimate value. Back in Chapter 8, that point estimate was a sample proportion, or the difference of sample proportions. In this chapter, it's going to focus on a mean. So the point estimate will be a sample mean. It'll be x bar, or it'll be the difference of sample means. It'll be x1 bar minus x2 bar. And then there's the third possibility that we didn't talk about with proportions, that we will talk about in video 3. But starting with our point estimate, we applied a margin of error that allowed us to add and subtract the same amount to both sides of the point estimate, and then that gave us our confidence interval. The whole goal of a confidence interval was to try to capture the true population value of interest. Now, in this chapter, we're trying to capture the true mean of interest. So let's walk through an example here. According to Nabisco, the average weight of an Oreo cookie is 11.3 grams. For the sake of statistics, we should calculate a 95% confidence interval to determine if their claim is plausible. After randomly selecting 30 Oreos from a large container of Oreos, you weigh each cookie to calculate a sample mean weight of 11.19 grams and a sample standard deviation of 0.0817 grams. Now, the sample standard deviation is going to be a new thing in this chapter because in our proportion chapter, we just needed the sample proportion, and we used it multiple times throughout the problem. But for a mean problem, we will need not only the sample mean, but we'll also need a sample standard deviation. So walking through the conditions, you're going to be like, these look awfully familiar. And two of them are, again, the same exact ones that we've been looking at for the past, 3 chapters at this point. So condition 1, the random condition. You have to be explicitly told that there's either a random sample or an SRS, or that an experiment would involve random assignment of treatments to volunteers. Now the independent condition, we're still checking, is the population at least 10 times our sample size? Remember, for the population, define who or what the population represents to the problem. It's all who or all what. And then tell me how much is the 10 times sample size value. For the most part, we will be assuming that this is true. And remember that the independent condition technically only applies when we sample without replacement, which is typically what we do, right? When we sample from a population, we don't put the things or the individuals back into the population for the chance to be reselected again. Typically we don't want the same person twice in our sample. So if we sample without replacement, we have to check the independent condition. Now, when we also are doing some sort of experiment and the people involved in the experiment are not randomly selected, if they are just simply volunteers, and if there's random assignment of treatments involved, then technically we don't have to check the independent condition either. So just make sure, if you have people that are being randomly selected, you will need to check the independent condition as long as there is sampling without replacement. If there is some sort of experiment involved, and there's only random assignment to our volunteers, then again, we don't need to check the independent condition. And then the normal condition. This is really what was different between proportion problems and mean problems back in Chapter 7 when we first introduced the idea of sampling distributions, because we did proportions and mean problems back in Chapter 7. And then in Chapter 8, we only did confidence intervals for proportions. In Chapter 9, we did hypothesis testing for proportions. And so it's been a little while since we've covered what the normal condition looked like for a mean problem. But the main idea applies here. We need to verify that the sampling distribution is approximately normal to allow us to calculate the critical value. Now, back in Chapter 8, when we did confidence intervals for proportions, the critical value was a z critical value, and we had to use inverse norm to come up with that critical value. Things are going to be a little different in this chapter with our critical values for means. Now, There's one of three scenarios that we're really going to need to check to validate the normal condition, and I would check them in this particular order. First, if the population distribution is given to you as normal, and they have to state it in the problem that the population distribution is normal or approximately normal, then all you have to write to verify the normal condition is the sampling distribution is approximately normal because the population distribution is normal. Now, how often is this going to be given to you? Probably not very often, but when it does pop up, this is going to be such an easy check. So again, first check, do they tell us anything about the population distribution? Is it approximately normal? Because if so, then this is all you have to write to verify that claim. Now, we also talked about the second condition here for the normal validation, and that was to use the central limit theorem. So again, it's been a little while since we've talked about the central limit theorem, but we needed a big sample size. We needed a big enough sample size. And we said in the back of our minds, we're going to keep that as 30 or more. You don't have to tell me 30 or more, but you do need to specify that you have a large enough sample size for the central limit theorem to apply. So number one, if the population is not known or is not approximately normal, then we check the second one. And if we have a big enough sample size, and that's the only thing we got to look for is that big enough sample size, then we can write the sampling distribution is approximately normal due to or because of the CLT, or you can write out central limit theorem with the large sample size N. So again, you have to mention those three things, that the sampling distribution is approximately normal. Why? The central limit theorem. Why does the central limit theorem work? Because of the large sample size. So those three components, in any order really, as long as you mention all three of those things. Now, back in chapter 7, when we did sampling distributions, this was where we stopped and we said either the population has to be given to you as normal or we have to try to use the central limit theorem. After that, we were out of luck. But I have more news to tell you. There's one more thing that we can check, and that's number 3. So if neither the first or the second apply, if neither the population is given to you as normal, or maybe we don't have a big enough sample size for the central limit theorem to apply, then we're going to need a graph. Usually I would recommend a box plot of the data to check for strong skewness and or outliers. Outliers is definitely going to be an easy thing to see in a box plot if we make the box plot with our calculator, because it will automatically determine if we select the right box plot option, it'll automatically show us if there are outliers present. Now, how strong is strong skewness exactly? And I'm glad you asked, because I'm going to show you some examples, and it's really it's not an exact science of how strong the skewness has to be. So let me show you 5 pictures here. And I'm not saying all 5 of these represent strongly skewed box plots. The first one's definitely not skewed at all. I mean, look at our 5-number summary here, where the min, the max, Q1, Q3, and the median, they are all nicely spaced apart. I would say this is very symmetric. Could it be approximately normal? Maybe, but it doesn't have to be exactly approximately normal. We could safely say, though, that it is symmetric. So strongly skewed, definitely not that. Now, on the flip side, the second in the middle here, I would definitely call this strongly skewed. So I'm going to highlight in green ones that I believe are strongly skewed. Now, let me talk about why I believe this is strongly skewed. What I look for. I look at primarily the minimum, the maximum, and the median. Because between the minimum and the median, this should be 50% of my data. So that little distance there is half of my data. And from the median up to the maximum, there's the other 50% of my data. And you can see that is not equal at all. I mean, it's not even close to being evenly distributed, right? Our second half of our data is very stretched out here compared to the first half of our data. So I would imagine this is very strongly skewed to the right. Now, you might also consider looking at, let me back this up here, I'll just clear this off here. You might also look at Q1, Q3, and the median. And the same thing applies here, right? I mean, here's supposed to be 25% of my data from Q1 to the median, and then the median to Q3, there's the other 25%. And again, it is really strongly skewed to the right. So both of those are allowing me to believe that this box plot, this data that this box plot was made from, is strongly skewed. Now, what about the third option here? And again, if I look at the minimum, the median, and the maximum, here's 50% of my data, here's 50% of my data. I feel like there is a very big difference between those. And so I'm leaning towards calling this strongly skewed. Again, if you want to look at Q1, the median, and Q3, and again, you can see, this is kind of like validation here. It is still strongly skewed, this time though to the left. So I would say that one is strongly skewed. Now, what about the one on the bottom left? Would we call this strongly skewed? And this one, I'm not as convinced, because if here's the minimum, the median, and the maximum, that 50% that's here, and then this 50% that's there, obviously it's not evenly distributed, but I don't really feel like this left side and this right side are crazily out of proportion like these two were up here. If you went to go look at, let's say, Q1, the median, and Q3, now you might go, well, look at that. That is definitely disproportionate. So to me, I don't know. When I, again, look at the min, the median, and the max, I'm seeing some skewness, but not what I would probably call strongly skewed. Q1, Q3, and the median, I'm definitely seeing some stronger skewness. So in all honesty, I personally wouldn't call this strongly skewed. But if someone wanted to use the argument about the middle 50% of our data being strongly skewed, I would, kind of buy that. But again, we really need to consider the whole picture here. I'm just kind of using Q1, the median, and Q3 as backup validation for the minimum, the median, and the maximum. So my initial gut reaction is, I don't think that's going to be strongly skewed. I think it's going to be skewed, but maybe not strongly. So this one, I personally wouldn't do it. But if someone said, I feel like this might be strongly skewed, I could kind of nibble on it. What about the bottom right? In the bottom right, I really don't. I don't know. This is kind of a toss-up for me. We've got minimum, median, maximum. There definitely is a very kind of disproportionate amount here. If I looked inside to Q1, the median, and Q3, it's not as bad in here, right? But would I call this strongly skewed? I definitely think it's skewed. I don't really know about strongly skewed. And I wish we would talk about a concept called kurtosis in AP Stats, which is an actual numerical value of skewness for our data sets. And so I feel like that would be a great number to bring in and say, like, if the kurtosis value was over this amount, then we would say it's strongly skewed. But we don't for whatever reason. So I would definitely call these two strongly skewed. These are a toss-up. These are maybe, but again, I'm not probably going to call either one of these strongly skewed. They have to be like so strongly skewed that there's almost an outlier present in here. Okay, so just keep these two pictures in your mind up here. All right, so if neither are found, if neither the strong skewness or the outliers are present, then we're going to write the sampling distribution is approximately normal because the data, or you could say the box plot, the graph, shows no strong skewness or outliers. And here's the thing. You have to include a sketch on your paper of what that graph, if it's a box plot, if it's a dot plot, if it's a histogram, whatever the case may be, whatever type of graphical display you want to have the data, you have to draw a picture of it to kind of indicate that there is no strong skewness and there are no outliers present in your data set. Now, before I jump to the next part here, a part of the you do in this video is going to be you're going to check the three conditions for our Oreo problem. So that's why I'm not specifically talking about the Oreo problem with our three conditions. I want you to validate the three conditions. So we move on to the calculations. So on the AP Stats formula sheet, you get this very generic formula here that it's the statistic plus or minus the critical value times the standard error of the statistic. The standard error of the statistic part, just like it was for proportions, is going to be given to you on the exam. So you get this very generic formula and you're going to get the standard error formula. You will just need to remember the statistic is either going to be X bar or the difference of X bars. The critical value is going to be, we'll start with Z. But here's the big problem. This sigma represents the population standard deviation. And in order for us to use Z, a Z test statistic, we have to know the population standard deviation. And to be quite honest with you, if we don't know the population mean mu, and that's why we're creating a confidence interval in the first place, we're probably not going to know the population standard deviation. But there are times where a problem will say, based on previous studies, we will use an estimated population standard deviation of this number. So if, for whatever reason, you are given the population standard deviation, sigma, if you are given that value, you're going to use the kind of standard, what we used all for proportions, the Z critical value, and you'll use inverse norm. But again, I'm going to tell you, you are not going to use this formula that often because you are not going to be given the population standard deviation often. So keep this in the back of your mind. This isn't going to be the normal formula we're going to use. We're going to use more this formula. And if we don't know the population standard deviation sigma, we're going to replace it with its next best thing, the sample standard deviation, which is just S, or in your calculator, if you did one variable stats, it would be that SX value. So if we use the sample standard deviation instead of the population standard deviation, then all of a sudden our critical value switches gears. It's no longer a Z critical value, but it is a T critical value. And we will have to use a T distribution instead of a normal distribution. Now, I just want to point out that X bar, S, and N are given to you basically in your sample information. You were specifically told about what the sample mean, the sample standard deviation values were for the Oreos. We were told how many Oreos that we dealt with. So we have these three numbers. All we're really going to need to figure out is what is that T value? How do we get that T value? So again, let me break down. When are you going to use a Z critical value versus when do you use a T critical value? So if sigma, the population standard deviation, is known, but this is rarely going to happen, you're going to go back and use that original Z critical value. So again, I would maybe say like in 1% of all cases, you might use this formula. You might use the Z critical value. But I would say most of the time, probably 99+% of the time, you are not going to know the population standard deviation sigma. So therefore, instead of sigma, we're going to swap it out with S, the sample standard deviation, and then we get to use a T critical value instead. Okay? So again, for the most part, T critical values for means. Now, let me show you what a T distribution looks like. And you're going to go, this looks a lot like a normal distribution. And I would agree. It does look a lot like a normal distribution. Now, every normal distribution and every T distribution still has to have an area of 1 or 100% beneath it. So you might go, well, look at this purple T distribution here. It's shorter, right? So if it's shorter, it's giving up all of this area to a standard normal distribution. But you just said that the area still has to be 1 or 100%. Where is that area that's, in between a normal distribution and a T distribution? Where is all that extra area going to? Because it's got to get redistributed somewhere. And then take a look at the tail ends. Notice at some point these distributions cross paths on both the left and the right sides. And notice, even though the purple distribution is the shortest distribution of these four, its tail ends are the biggest. So that extra area that's in between the normal distribution and that lower T distribution, it gets made up for on the two ends of the distribution there. So again, it's got to be 1 or 100%. And if it's shorter in the middle, it's got to be fatter on the outside. If it's taller in the middle, then it's going to be shorter on the outsides. Now, t-distributions are unique in that there are different t-distributions depending on the sample size. And in order to differentiate all those different t-distributions, we don't normally use the sample size itself to distinguish them, but we use this concept called degrees of freedom. And the degrees of freedom are really based on the sample size. So a t-distribution has degrees of freedom. The degrees of freedom are just the sample size minus 1. So if I had that purple t-distribution and it says this is a t-distribution with 1 degree of freedom, what's the sample size? Well, if there's 1 degree of freedom, the sample size must have been just 2, right? So the smaller the sample size, the smaller the degrees of freedom. The smaller the degrees of freedom, the shorter that t-distribution is. And so now here's where this little note comes into play that I wrote off to the side. Notice what happens when a t-distribution gets its degrees of freedom to be bigger and bigger and bigger. And for the degrees of freedom to get bigger and bigger and bigger, the sample size has to get bigger and bigger and bigger. So the purple goes to the blue, goes to the orange. And so as our degrees of freedom get bigger and bigger and bigger, notice it's getting closer and closer and closer to that standard normal distribution. Will a t-distribution ever get past a standard normal distribution? It will not. For my calculus-minded people, the limit of a t-distribution as the sample size approaches infinity, or as the degrees of freedom approach infinity, ends up being the normal distribution. So a t-distribution gets closer and closer and closer, but never fully gets to a standard normal distribution. Now, the other thing I want to show you, because in this one I showed you, the green's the standard normal, and then the orange was a t-distribution with 10 degrees of freedom. Here is now a picture of a standard normal with a t-distribution with 30 degrees of freedom. And notice there is not a whole lot of difference between those two things. But still, notice the t-distribution is technically underneath in the middle here of the standard normal distribution. But what's nice is if you think about 30 degrees of freedom, that would mean the sample size had to be 31. And what happens when we have sample sizes that are 30 or more? The central limit theorem kicks in. And so this is kind of like the central limit theorem at play for t-distributions. If our sample size is big enough, the t-distribution and the normal distribution are nearly identical to each other. There is not going to be that much difference in our critical values. All right, so back to the calculations. If we use our x bar plus or minus t critical value times sample standard deviation over the square root of our sample size, again, we know the sample mean, we were given this number. The sample standard deviation, we were given this number. The sample size, we were given this number. The only thing holding us back is how do we actually get that t critical value? Because I haven't mentioned anything. I've mentioned what a t distribution is, but how do we get that number? And so in a very similar sense to how we got z critical values with inverse norm, we're going to have to use the next calculator command in our list. So now to get the t critical value for our 95% confidence, we're going to go to second variables and get our inverse t command. And for area, we're going to throw in one tail area. So for a 95% confidence level, there was 5% left over. Half of that gives us 2.5%, so 0.025 for 2.5%. Degrees of freedom is our sample size minus 1. So sample size is 30 minus 1. We have 29 degrees of freedom. So put in 29 there, do paste, press enter. For the older calculators, you may not have inverse t. I may have to give you that particular program so that you are allowed to use the inverse t function. But if you have inverse t, and it looks more like this instead of the menu option, you're first going to put in your one tail area, 0.025, then a comma, then your degrees of freedom in the parenthesis, press enter, and you will get negative 2.045, yada, 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 yada. Remember, we drop the negative. We don't care that our test statistic is negative, but I want to keep these 4 significant digits. Now, if you did 2.05, that's okay. If you did 2.1, you're getting kind of borderline rounding too much there. So at least 2.0, I guess 5 would round to 2 decimal places, 2.045 to 3 decimal places. So once we go plug in now all of our numbers that we now have into our formula, then we can do our calculation, just slowly but surely break apart the plus and minus, and we should get a confidence interval of 11.159 to 11.221. All right, now if instead of using the formula, you want to use the calculator command, right? A lot of you guys have been wanting to use those calculator commands because it makes the calculations go by so much quicker. So the proper name of this procedure is a one sample t confidence interval for mu, or for a mean. Not a sample mean, but technically a population mean. But if you just say a mean, we're going to imply a population mean here. Now, what if they give us the population standard deviation sigma? Well, then you would do a one sample z confidence interval. But again, for the most part, we are going to be doing a t confidence interval. So if you press stat, go over to test, start scrolling down, we are predominantly going to use this number 8 option, just a t interval. Notice there is no one t interval like there was for, let's say, a one prop z int when we did proportions. So you're not going to see mean used at all to describe a calculator command for a mean. If it says prop in it, then you know it's going to be a proportion problem. But if it doesn't say prop, then that's your hint that it's really going to be for a mean for the most part. Now again, I mentioned if it was just happened to be a z confidence interval, then you would technically use option 7. So if I select number 8, and here's one thing we're definitely going to have to kind of explore the difference of, is what kind of values do you have? Do you have the raw data, or do you have statistics about your data? So it kind of depends on the problem, and we're going to explore both of these. But just for video 1, we're going to explore the statistics part. The statistics was given to me. I was given the sample mean of my 30 Oreos. I was given the sample standard deviation of my 30 Oreos. N is 30 Oreos, and my confidence level was 0.95. And then I can press calculate, and I get my confidence interval right here. And that's really the main thing I need to write down. So if I want to use my calculator command, remember, you have to properly name the procedure in words here, and then come up with the confidence interval, and you're done. Now, the conclusion is the same old conclusion that we wrote about before with proportions. We are 95% confident that, but this time, instead of it being about the population proportion, it's about the population mean, and we were looking at the mean weight of an Oreo is between 11.159 and 11.221 grams. Because again, those were the two numbers that I got from my calculator. Now, the 3 you do parts here. I want you to verify as many of the conditions as you possibly can. And if you can't verify one of the conditions, then what would you need to know in order to fully verify it? The second you do problem was, what is a t critical value for 99% confidence with a sample size of 50? So you get to practice getting a t critical value. And number 3, according to Nabisco, the average weight of an Oreo cookie is 11.3 grams. Now, using the confidence interval that we just calculated earlier, is Nabisco's 11.3 gram mean weight of an Oreo plausible? Is it a plausible value? And you might kind of think about how that ties into hypothesis testing, which we'll get back into next chapter. So think of this as their claim. This is like the null hypothesis. So should we reject or fail to reject this 11.3 gram claim using the confidence interval? So we'll talk about those the next day in class.